Hey there, you're it's Mr. Herman here, and this is lesson 4C, area of basic shapes. Learning goals for this lesson is to understand what the area of a two-dimensional shape is, and to also understand that the area of composite shapes can be found by adding or subtracting the area of more basic shapes. And we'll be looking into what a composite shape is later throughout this lesson. The success criteria for this lesson is to be able to convert between different metric units of area, and to be able to find the area of basic shapes such as squares, rectangles, parallelograms, and triangles. Now, before we delve into this exercise, I'm going to start this lesson with a starter question. And although this does have to do with volume, it is a good segue into how the area conversions work. There is a prize involved with this when we go back to face-to-face teaching. The first person to answer this question correctly after they've watched this video and have sent me a team message, if you get it correct, you will get a chocolate when we get back to school. A whole bar, actually. With this in mind, you only have one opportunity to give me an answer, okay? You can't just keep guessing until you get it correct. You've only got one shot. Here is a question. Here we have one of these little wooden cubes, and I've blown the size up. The size of this is 1 centimeter of width, 1 centimeter of length, and 1 centimeter of height. Now, I got a picture here that you can see right there of what you guys maybe could have played with when you were in primary school to understand addition and multiplication. I know I did play with this when I was a bit younger. And this was a good representation of how multiplication works. Now, this does segue into volume. And this right here is it does say cardboard box within the question, but I couldn't find a picture of a cardboard box on Google Images. So I've used this, this image here. This right here is a box that is 1 meter by 1 meter by 1 meter. So width 1 meter, length 1 meter, and the height is 1 meter. Now the question is, how many of these little cubes can fit into a box exactly 1 meter by 1 meter by 1 meter? Now, a little clue is that there are 100 centimeters in 1 meter. Now remember, we're also getting the volume. We're getting the length, width, and height of this. So take this into consideration. Give me your answer on Microsoft Team chat. Only one guess per person, and whoever answers this question first will get a chocolate prize when we get back to face-to-face teaching. For now, we are going to head into the actual lesson itself. And right now, we're going to go into metric units conversions. Now, before this, we looked at how to convert from millimeters to centimeters to meters and kilometers. Now, we're trying to convert from millimeters squared to centimeters squared to meters squared to kilometers squared. And what these little twos mean, these little squares, just necessarily mean is if we have a shape of some sort that is a square that's like that, and let's say this is 1 meter and this is 1 meter. A question could be, how many of these 1 meter by 1 meter squares can fit into an oval, an MCG oval, like this? And you can make these different estimations. Obviously, it's not going to be precise because the oval is an oval shape and this is a square shape. But this right here, what you lay down onto the field, this is area. This is what we consider as area. How many of these, when laid flat, could fit into this? Or how many of these smaller ones, 1 centimeter by 1 centimeter, little squares, can fit into a shape like this? Or even we can go one step further, how many of these 1 millimeter by 1 millimeter squares can fit into this? And you're expecting that this will be way more than this, or even this. How we do these different types of conversions, or how we can figure out certain conversions of squared units can be used by using this table, which looks very similar to the previous table that we saw. The only difference is what you're multiplying by or what you're dividing by includes more zeros. So how you would read this is if I wanted to go from meters squared and I wanted to convert meters squared into centimeters squared, I would just multiply this by 100 to the power of 2, or 100 squared, or 100 times 100, which is 10,000. So what this actually means is, in this case here, this right here is a meter squared. Okay, this is a square and it's in the shape of 1 meter by 1 meter. If I wanted to work out how many centimeters squared are in this, and obviously this is not to scale, I have to get this amount, which is 1, and I need to multiply it by 100 to the power of 2. This is just indicating that there are 10,000 smaller centimeter squares within here. And that makes sense, because if 100 meters, if 1 meter, sorry, is the same as 100 centimeters, and this is the same as 100 centimeters, then the area of this is length times width, which is 100 times 100. Hold on a second, that's the same thing that's going on here. There's a link between the two. So if you don't want to confuse yourself, all you need to do is just follow the arrow that you're going from to the next one. If you're going from left to right, you're going to use multiplication. And if you're going from right to left, you're going to use division. Just make sure that you use the correct number. If you're going from one to another and they're two positions away, you will need to do a segue into this one first before you get to this one. We'll look into some examples to get a better intuitive feel of how to tackle this. The other thing we'll be looking into is the areas of basic shapes. Now the areas of these basic shapes over here: a square, rectangle, parallelogram, a triangle, and another shape called a composite shape. And a composite shape is just a combination of the basic shapes that you see above. So the first one is area. The area, I'm going to put little letters here. A just means area. Instead of writing area equals, we can just write A equals. This is a shorthand notation. So A is equal to area, and the square area is L times L, or L squared. L in this case is the length. So whenever you get a square, get its length. To get the area, or to find out how many smaller squares can fit into there, just get L and square it, or times it by itself. And this is why that little 2 is called squared. It comes from the fact that you're finding how many squares are within a square, how many smaller squares are within a bigger square. So that's where that square comes from. And then the L to the power 3 is cubed. That has to do with volume. It's called cubed because you're dealing with cubes, but we'll look into volume later down the track. For the area of a rectangle, this is L times W. W standing for width. So if you can get a rectangle, you give me the length, you give me the width, just multiply the two numbers together and that will tell you how many smaller squares can fit within a rectangle. A parallelogram, without going into the reasonings behind why this works, the parallelogram is B times H. So area is B times H. B is the base of the shape. So the base is always the bottom line, and the height is H. So this here is height. Now it says a little note here, the dashed line which gives the height is perpendicular. I always struggle with that word. So perpendicular just means that at the base it creates a 90-degree angle from the base to get its height. So your height isn't going to be this length here. That's not the height, that's the slant of the shape. It's not going to be from there to there diagonal. It has to be exactly 90 degrees of where the base is. And you've got to keep this in mind when you're using this formula, because sometimes they will rotate the shape and it's a bit tricky to determine what the height is. We'll look into an example of that as well. The triangle has the following formula. The area is equal to half times base times height. So they have here half. So halving it, you can also divide it by 2. get the base, get the height, and then divide it by 2, or you can do half times base times height on your calculator. Both of them will work. Again, we'll look at another example for this. And the last one is areas of composite shapes. These can be found by getting this particular example anyways. You get the area of shape 1, which is a rectangle, get the area of shape 2, which is a triangle, find out the areas separately, and then add them together. There will be a case which you might need to subtract one area from another. We'll look into that later down the track. So let's put these different key ideas into play. Let's see what we can do in order to tackle these questions using the previous key ideas and formulas that we just looked into. First one is we're going to convert units of area. We're going to convert these area measurements to the units shown within the brackets. So the first one is we're going to change 0.248 squared meters into centimeters squared. So let's go back. We're changing from meter squared to centimeter squared. So let's go back. We're going to look at meter squared and centimeter squared. So this is our starting point and this is our ending point. In order to get from one to the other, just like we did in the previous example, we need to times this by 100 squared or times this by 10,000. So A, this is going to be 0.248 times 10,000. This is going to say that 248 squared meters is exactly the same as, so let's go get my calculator. Alright, here's a trusty calculator. 0.248 multiplied by 10,000, and this is equal to 2480. So if you're just blindly doing this and you're thinking, what is going on? Let's say, for instance, that you had, I'll try to draw this in 3D as best as I can. So right here, this is a meter by meter area within the ground. So a meter, you can think of just taking a large step forward and then turning and then taking a large step forward that way. And it creates this square. Now 0.248, which is close to 0.25, which is approximately, say, a quarter of that amount there. It's roughly 0.28. Yeah. Okay, so 0.248 squared meters. Okay, it's less than 1 because it's a decimal. And this is saying that, well, how many centimeter squares, so how many small centimeter squares can fit within this little area in here? Well, after the conversion, we know that 2,480 of these can fit within there. That's what this question is saying. That's the visual side to it. But all you have to simply do is just get the right conversion, follow the chart, and go from one to the other. Let's have a look at the second one. So for B, we're changing 3,100 squared millimeters into centimeters squared. So millimeters to centimeters squared. Go back to our trusty chart. Millimeters to centimeters. Oh, it's going too far. Oh my goodness. There we go. Millimeters to centimeters squared. We are backtracking. So we are dividing by 10 squared, or we're dividing by 100. So to get millimeters to centimeters squared, let's get 3,100. And we're going to divide this by 100. Just had Monty walking in, giving me a little bird thing that he made. See if I can take a picture of it and upload it later. So 3,100 divided by 100. That's my wife saying there's a garbage truck. This is equal to 31. So 3,100 squared millimeters is equal to 31 squared centimeters. That's all there is to it, just using that conversion chart to help you out. Alright, basic shapes. We're going to use the formulas that we saw before, just to get a better, no, not to get it better, but just to actually tackle these type of questions. So A, we're going to find the area of this rectangle. So this is saying that this rectangle is 6 centimeters across, then 2 centimeters as height, length, width. All we need to remember is length times width, or in this case, 6 times 2, which is equal to 12. Now, you don't leave the answer just as 12. There are two things you need to consider. The first one, if it has a unit of some sort, put the unit with it. Because we're dealing with centimeters, we need to write centimeters. And because we're dealing with area, we need that little 2 there. That 2 indicates that we are dealing with 2 dimensions. 1, 2. If I were to draw this up, what does the actual area mean? If I split this up into, roughly, not to scale, to 6 sections across there, and 2 here, we're finding how many of these squares can fit into a rectangle this size. Well, this is 12, which is just 6 times 2. This is what area is. How many of these little squares can fit within an enclosed shape? B, the area of parallelogram is equal to base times height, B times H. Now you'll notice that the base is a bit tricky to find because we're used to the parallelogram within the other example, it being lying down on the ground or on the floor. Here it's this vertical height. But even though this is vertical, it is still considered the base because we can just change this or rotate this around to have the parallelogram lie on the ground. So in this case here, our base is 8. And the perpendicular height, so the height that runs at an exactly 90-degree angle of this is 3 meters. And it's exactly 90 because you can see a straight line going horizontal. 8 times 3 is 24. Again, we need our unit, and we need a little 2 to indicate that we're dealing with area. So it's 24 squared meters. So in other words, 24, if this was an 8 meter by 3 meter parallelogram, exactly 24 squares in the form of 1 meter by 1 meter can fit within this shape. So the last one here, C, we have a triangle, and this is equal to half times base times height. That's from the formula we saw before. So half times our base in this case is 13, and our height is 7. Now, I have students asking, where does this half business come from? Why is it half? And the reason is because a triangle is always half of the shape of a rectangle. So if you can find the base or the length and the width of a pretend rectangle, if I were to fill that up here and fill that up here, here's our rectangle, here's our length, here's our width, so it's 13 times 7, but we're not including these lengths. So we need to half it to get the area of exactly here, which is a triangle. So that's where that half comes from. So half times 13 times 7. Let's grab a trusty calculator if the calculation's a bit too tricky. Fraction 1/2, or you can put 0.5, that also works as well, times 13, multiply by 7, we get 45.5. This is in meters, and we need a little square symbol. Now, because you guys are in year 8, this is a lot of the area type focused work is a year 7 work. We're going to stray a bit further into composite shapes now, and how we can use the basic formulas from the previous examples to work out more complicated, interesting looking irregular shapes. So right now we have got this composite shape here, which is made of a rectangle with a triangle that's kind of cut out into it. Now they kind of put this form of a triangle within here by putting this dashed red line horizontal that goes across and a vertical one that goes down to indicate that, hey, we're dealing with a triangle here. So what we need to do is, the first thing I always do is label this shape 1 and label this shape 2. So I know what we're dealing with. And what we need to do is work out what area shape 1 is, which is the whole rectangle, and take away area shape 2, which is this triangle here. So let's work out area 1. Okay, so area 1, and area 1 is just a rectangle, which is just length times width Our length is 10, and our width is 6. So it's just 10 times 6, which is 60 squared meters. So this is making the assumption that we've got this whole rectangle here, which is 60 square meters. But we don't want the whole rectangle, we want just the portion in here. So we need to find out this area here, this triangle, and subtract that from 60 square meters to give us the remaining area that's left over. So area 2, let's work out area 2. Area 2, this is equal to this triangle. Now we got to do a little bit of investigating here to see what measurements we can get from this. So we know what the area of a triangle is. It's half times base times height. We need our base. So the base is that floor part. So this is kind of flipped upside down. So our base is that length from there to there. I already know what that length is. That length is the same length from here to here, isn't it? Which is 10. So there, our base is 10. And the perpendicular height, or the height of the triangle, is this small little dotted dashed line here, which is in red, which is 4 meters. So we're trying to find out half times 10 times 4. I don't need a calculator for this one. 10 times 4 is 40. Half of 40 is 20. So area 2 is 20 square meters. So to get the area of the composite shape, so the area of the composite shape, or the overall shape, is equal to 60 square meters take away 20 square meters, and this right here will give me 40 square meters. So in other words, this area of the composite shape right there, we take the biggest one and subtract the smallest one, will give us 40 square meters. Last question here. We have another composite shape type of question, but this time this is a combination of a square and with a mini rectangle attached to it. So I'm going to label this one area 1 and area 2. I'll put a line here to indicate that that is the part of the question. So area 1 is just length times length, or length squared. And this is just equal to 3. Now, what's this length here? I know that this has to be 3 because of the 2 dashed lines here. This is an indication that anywhere I see 2 dashed lines, if one of them says 3, then all of them will have to be the same size. So in this case, it's 3. So this is 3 squared. And remember, 3 squared just means 3 times 3. So this gives me 9 squared millimeters. Dealing with millimeters, and we're dealing with area. So there's the first one. Area 2. We need to work out now that area of the small little rectangle. This is a length of 1 and a width of 1.2. So this is length times width, which is equal to 1 times 1.2, and that's just simply 1.2 squared millimeters. Now, to get the area of the shape, in this case, we just need to add them. We just need to add the 2. So this is equal to 9 squared millimeters plus 1.2 squared millimeters, and the overall area of the shape is 10.2 squared millimeters, and that right there is the area of this composite shape. So composite shapes are not that tricky. Sometimes you might need to investigate a little bit more in order to figure it out, but all measurements will be given to you regardless. So the questions that you need to do from exercise 4C is on page 208. You will need to attempt question 1. You don't need to do question 2 because this deals with hectares and we're not dealing with hectares. Question 3, I would like you to do the 2 left-hand columns of question 3. You don't need to worry about the right column there. So 3A, B, D, E, G, H, J, K. And question 4, I want you to do 4A, B, and C. Best of luck, guys. If you have any questions, you know where I am. I'll see you in the next video. Bye-bye.